Hi everyone, and welcome back to another instance of Math Research Live with me, Charlotte Aten. So, if you were following along with me last week, I was I was going through this paper that gives a formula for the number of Latin squares of a given size, and my goal was to generalize that formula to a similar one for higher dimensional Latin cubes. Or Latin hypercubes, maybe. So this week I'm going to continue on with that. So I'm actually going to just briefly go through what I had last time. I actually, besides the fact that I have more than enough other things to do besides this project that I've been messing around with, I really made a concerted effort not to think too hard about any of this or to look at it again during the course of the week, so that as close as possible you can actually watch me in real time go through doing this process. Of course, it's a bit slower than what it would look like if I was really doing it just by myself, like for myself, because then I wouldn't be explaining what I'm doing. I would just be sitting there and thinking about it and trying stuff, which goes faster. I do talk to myself a little bit, but not too much. But yeah, hopefully, we'll pick up where we left off. And if this is, your first time and you haven't seen me working on this before, that's okay. Just ask questions, and I'm sure that we'll still end up seeing some new stuff, regardless of however many questions there are. So, yeah. So I hope that people are ready to check it out and have been having a good week. Let's see. Oh, yeah, and I guess I'll mention too, I'm actually teaching at CU Boulder now, so today was my first day of class. It was everyone's first day of class, I guess, as long as, you had class on a Monday. So that was really cool. Definitely excited to be at Boulder. I'm teaching linear algebra this semester, and while this does have something to do with linear algebra, I'm thinking that if I do happen to have any students from my class watching, this won't be very similar to anything that we're doing in the linear algebra class. Yeah. Okay, so last time I said that there was this formula. Oh, and I have the paper linked in the chat as well. So there was this formula that was given in this paper by Xiao and Wei from 1992, I guess, 1990, something like that, where they gave a formula, which is here, for the number of Latin squares that have a given number n of rows and columns. And so last time I went through just kind of looking at what each of the parts of this formula meant, and also kind of discussing where it was coming from. And so I'm going to remind us and myself of that, and then I'm going to actually look at how I can generalize this to counting a similar kind of object that's a higher dimensional version, basically. Yeah, so again, just let me know if you have any questions about anything or comments. We also have a fun emoji that is a 3-hole donut emoji if you're feeling a little more topological today. I guess this is a lot of more like combinatorics, but it's not the absolute value of the determinant. So I'll remind you of what it is. Here, let's go to that part first, because why not? So there were many things that we talked about, but let me. Okay, so is this formula? Okay, so this is the. Oh, okay, yeah, but it's like take the absolute value of each of the terms, right? But that's different from the absolute value of the determinant, because right, like so. The determinant of a 2x2, matrix is going to be like this, AD minus BC, but it's AD plus BC. But of course, if we say, well, yeah, let's see. So, well, the determinant of this is 0, that's also 0. Okay, I guess I don't have. Oh, okay. Here's a good example. I was looking for an example. So, the determinant of this matrix, that is the all one matrix, the determinant of that matrix is 0 because it has two. Its row space is not is not everything, right? Like it's just got the same thing. Or okay, this is actually like what I would cover at some point in my linear algebra course, but if we look at the rows, say, of this matrix, they're not linearly independent, so it's going to have 0 for the determinant. But on the other hand, the permanent is 2, so it's definitely not the absolute value. But as long as you remember, when you think of it as like the absolute value of the determinant, you remember that it's really just changing all the minuses in the formula to pluses, and that's good. But yeah, so yeah, again, feel free to just ask whatever. So it looks like I'll just kind of go through my notes that I had from last time. It looks like we talked about counting how many magmas there were, and we had like a bit of a sidebar, which I won't get all into again, but about like what counts as being like two equivalent magmas. Like what do we mean by two things being the same? Like is it just whether you can relabel them or like different things? And so I talked about what it meant for two magmas to be isomorphic, which is basically this idea of being able to relabel them. Actually, I've never read Axler. I don't know it to have. I don't have anything against it necessarily, but I think there's a standard algebra text which is Axler. So I'll say this: any standard algebra text, undergrad or graduate, like abstract algebra, will talk about the notion of isomorphism. I'm not sure whether magmas will be covered. Many sources do start, if not start with magmas, at least talk about magmas at some point, just because that's kind of the general abstract setting where a lot of, these first things that you learn, you can see examples of, maybe without worrying so much about the axioms of groups or rings or whatever to begin with. Yeah, I mean, certainly like the idea of isomorphism should be covered in any, that's intro abstract algebra. Is that your question? Just like, is isomorphism covered? Or, oh, the permanent. Actually, I'm not sure. So, it's a good bet that it's in Lang, because Lang wrote his books by, at least this is what I heard, this is like third-hand information, but Lang apparently took all of the books that he could buy on each subject, and then he just would make an encyclopedia that had all of the results and definitions and everything from those into a book, and then that's the book. So I don't specifically recall the permanent ever being covered in any like linear algebra or abstract algebra course that I ever took when I was a student, but it is it's possible that it's in one of these, and I just haven't happened to look at it. I would imagine that a book on multilinear algebra would probably have it too, because like something like this might appear in the discussion of if you define the determinant as being like the unique alternating multilinear form that sends the identity matrix to 1, then you might want to talk about something similar where instead of being alternating, it's a symmetric multilinear form. But yeah, I can't say for sure. My understanding of the permanent basically comes from seeing it in this paper and then looking it up briefly on the internet and understanding the definition and then saying, yes, it's like the determinant without the minus signs in the definition. So I'm happy to, I'm happy to, yeah, so the thing about Lang is, like, you can, like, okay, I don't recommend just trying to read, like, one of Lang's algebra textbook, like, just to read it, like, through. They're great if you just want to look something up, but, like, he's, in my opinion, I don't remember, it's been a while since I was, actively, like, taking my graduate algebra courses and stuff, then we were using Lang, but, I don't remember, like, like, I still refer to Lang from time to time, but it's not something that I don't remember ever sitting down and reading any, like, you know, reading his algebra text and being like, oh yeah, I'm having a great time reading this exposition. It's more like, oh wow, I'm really glad that I already understood the idea behind this, and I'm just looking up some more information, because if I wasn't, then but it's, I don't know. I don't remember exactly what he says in the introduction to it, but I feel like he sells it as like it's like a textbook, but it's like one of these things where like you're not seeing any of it. You shouldn't be seeing that much of this for the first time, or you're not going to be able to understand it. Like, you have to start on a more introductory book, and then, you know, then you're seeing it again, and it's an encyclopedia. Maybe it's an encyclopedia masquerading as a textbook. Well, anyway, so I talked about this. You know, there are lots of magmas not up to isomorphism. So we talked about that. I talked about what a Latin square was. So, like, for instance, this is an order 3 Latin square. Each symbol appears once in each row, in each column. But this thing over here is not a Latin square, because this column over here has two 3s, and so 3 appears too many times. And just ask again if you ever forget what any of these things are, and I'll remind you. And so a quasi-group is just a magma whose multiplication table is a Latin square. And so we just can think of Latin squares as being like multiplication tables as well. Yeah. So we can use the notion of, if we wanted to, we could use the notion of isomorphism of magmas to also talk about when two Latin squares are isomorphic by viewing them as quasi-groups. So, here we talked a little bit about the relationship between having division and having inverse elements. So I'm not going to go over the whole thing again unless someone's really curious. You can also go and watch the recording on YouTube from last time. So there was that. And so then I got to the formula, and it took a lot longer than, it's been like 12 minutes now that I've been doing this. It took a lot longer than that last time. So when we get to the formula, this is telling us, we have a few expressions in here that are things that we need to know what they are. So this B sub n are the n by n matrices whose entries are all zeros or ones. This sigma naught of A is the number of zeros in the matrix A. We talked about the permanent. And so if we know what all these things are, we can use this formula. And so I actually did some calculations where I said, okay, let's do this when n equals 2, just to make sure that it makes sense when n equals 2. And so when we looked at this, you know, for each of these matrices, you know, that are in this set B2, like the all zero matrix, these ones, and so forth, I didn't write them all down. You know, I checked how many zeros are in it, what's the permanent, and pretty quickly I realized, well, you know, unless the permanent is at least 2, then we're just going to get 0 for that permanent choose 2, and so this part's going to make everything 0. So the only term that actually survives is this one, that is the all one matrix term, and there sigma naught is 0, the permanent is 2, and then we end up getting that it's just this 2 factorial. The sum really just becomes this single term, minus 1 to the 0, 2 choose 2. Well, that just gives us 2, and we actually see there are only 2 Latin squares of order 2. There's this one, and there's this one. And remember, we're not counting them up to isomorphism, so if they look different, they are different as far as we're concerned. So the formula works when n is equal to 2. And then I started looking at n equals 3 a little bit, just for more of an example. And I said, well, okay, let's look at you know, the same kind of table. But clearly, if we have stuff that's going to be like permanent of A choose 3, then the permanent of A is going to have to be at least 3, or else you're not going to get anything. So you know, we had seen here for the all 1 matrix, we get permanent 6, so that definitely works. But even for some matrices that aren't all 1s, like this one, we have a permanent of 4, which still works. And so we need to figure out which permutation matrices. Oh, hi, hey, welcome to the stream. I hope you've been having a good week. I'm just I'm at this point I'm just going over what we did before, and then I'm going to start trying to finally generalize this formula. And as always, just feel free to ask me if you want me to remind you what something is, or what we did last week was something, and I will be happy to do so. So I looked at, you know, the example of using this formula up here, but when n is 3, and we saw that since we have these terms that have permanent of a choose 3, that's only going to give us something when the permanent of a is at least 3. And so there are some different terms that show up. Oh, are you saying that the author was sneaky here and just writing for all A's instead of writing like for all the A's, so that the permanent of A is at least 3 or something like that? Is that? I think that might maybe what you meant. Because yeah, it would be I don't know how difficult or annoying it would be exactly, but we'd have to sit down and think about, like, well, how do I actually describe which of these matrices in Bn are the ones that are have permanent, which is at least n? And the authors of this paper didn't worry about that at all. They just kind of said, you figure it out. If you get one of those matrices where its permanent is less than n, then you just don't have that term, and it just gives you 0. So yeah, that was a little bit of them. They're pushing work off onto us, right? They're saying, okay, you figure it out. It'll just, those don't really affect anything anyway. But if that's not what you were thinking, let me know, because that's what I took from it. There's a lot of this type of thing in math, you know, where somebody figures out a way of pushing it off on you, and they say, okay, I figured out this part, but, like, you know, if you actually want to use it, you're going to have to do some more work. I don't want to do that. Okay. So, yeah, that was that situation. And then, okay, and so then I started talking about what these Sij were that were in the paper. Oh, okay, that was it. So if we go back to the paper for a minute, maybe, as I mentioned before, there's a link to this in the chat, or at least to a Science Direct page. I couldn't find just a direct link to a PDF online, but either just, you know, I don't know, you know, take a screenshot or whatever, or just open up the other video and pause on it or something from last week, or, you know, whatever. So in order to do this proof, which I'd like to generalize, they use these sets Sij. And so the idea was that having an n by n Latin square was the same thing as having a list of n by n permutation matrices, which told you where to put each of the symbols in the Latin square. And I'll remind you of what that correspondence looks like over here. So I actually did an example at the beginning for my intro to the stream thing. So you can think about this as these 3 matrices. This first matrix tells you, like, where you should put the 1s in this table up here, or 0s, I guess. Okay, wait, I have an example that uses the symbols 1, 2, and 3, I think. Let me not confuse it by using the symbols 0, 1, and 2 in addition. I think I have a different example. Oh yeah, okay, so down here I said, okay, we have this Latin square, or this quasi-group, and I can make a matrix that says, where do the zeros go in the table? Well, there's a 0 in the top left and the bottom right, so I'll put 1s there. Or, sorry, where do the 1s go, rather? So there's a 1 in the top left and the bottom right, so I'll put 1s there. And then I can make a different 0, 1 matrix that says, where do the 2s go? And I can put a 1 in that matrix wherever there's a 2. And so the idea is that, well, specifying where each of the symbols goes in each row and each column is the same as figuring out, you know, is the same as telling you all of the info about the Latin square. So In other words, having a Latin square is the same thing as having a collection of permutation matrices where they add up to be what I call this J2 or Jn, where it's the all one matrix. And so you can do this even for bigger Latin squares. I guess I didn't do another example of that besides the previous one that I decided I didn't want to talk about because it had the different symbols that weren't 1, 2, 3, and so forth. Maybe I did a different example down here. Oh, I guess I did a non-example. Alright, well anyway, well, I'll stop being lazy and I'll do another one. Let me give you a slightly bigger example just to you know, illustrate it further. Suppose I had this Latin square. I can think about just to verify that yeah, so actually it does a couple things for us. So the reason why this correspondence like goes both ways is because on the one hand, if I have a Latin square and I make these matrices, like I can say where are the ones, they're here, and then I can say, you know, where are the twos? Well, they're at these locations, and then finally where are the threes? Well, they're at these locations. Oh yeah, they're at these locations. And then if you add these up, you get the all one matrix, 3 by 3 all one matrix. And so the reason that you know this correspondence goes both ways is, well, okay, certainly you can believe that, you know, if I have a Latin square, then I can make each of these permutation matrices, and then you can see that they would have to add up to the all one matrix because, well, if there's a 1 here, that means that we have, oh well, let me do a different symbol, it's not 1. So if we have a 1 here, that's telling us that there has to be a 2 here in the Latin square table. And so there shouldn't be any other 1s in that spot in these other permutation matrices, because then there would be another symbol that was trying to also be there, and that can't happen. So we should only get one in each of the entries, so when we add them up we should get the all one matrix. And these have to be permutation matrices, because if they weren't permutation matrices, then we would have either a row that was like maybe all zeros, and then there wouldn't be a symbol at all in that row that was of the given type, or there would be a row that had more than one in it, and then there would be too many of a symbol, say, in that row. You know, so it we definitely have to get this from each Latin square. But if we go back the other way, then if you have three permutation matrices like this for the 3 by 3 case, well, the fact that each of these is a permutation means that the same symbol can't show up twice in any row or any column, and having that they add up to the all ones gives us that there is at least one symbol in each row and each column, and so altogether that tells us that we have what we want. So yeah, this is an exactly equivalent thing to being a Latin square. Because of course, you know, if you have something like this, you know, if I just only take 2 of the matrices, but I don't ask that they have to add up to the all one matrix, well, in this case, you know, for instance, I could just have that, you know, there's no, it'd be like just not having the symbol 3 in there, and then I would just be missing that. So I'd have like 1, 2, and then just nothing here, 1, 2, you know, oh, no, I don't have the 3, you know. Oh, sorry, my 2s and my question marks look similar. Hopefully you can see the difference. Okay. Well, in any case, yeah, so having n permutation matrices that add up to the all one matrix is like exactly the same data basically as having an n by n Latin square. Okay. And so, well, if we know that, then the idea was that we're going to want to work with these sets Sij, where what these are is they're saying they're lists of such permutation matrices. So they're lists of those permutation matrices. There are exactly n of them if we're doing n by n Latin squares. And the condition is that if we look in the ij entry, like say the 2, 3 entry, some specific entry for each of these, they're all 0. So if you think about it, maybe I'll go back to that example I was giving. If you think about it, that would be bad if that was the case, because say if we had a 0, say in the well, okay, like take this example where we still would need to have another matrix here of some type, but there. Yeah, so there is a sense in which these two ideas are like isomorphic to each other. So one way that you could do this is that if you wanted to, on the one hand over here, you can think of there being, well, I guess actually let me ask, have you seen what a category is before? Or were you here for that conversation last time about that had to do with, well, it was related to the idea of isomorphism for these things? Because if you know what a category is, it'll be easier for me to tell you what I want to tell you, but I can still I can also not use the word category and still say about the same thing. Well, okay. So the idea, I mean, which you can follow this if you don't know the word category too, I suppose, but it'll make more sense if you do, is that these Latin squares over here have a notion of not just isomorphism, but what's called homomorphism. You can think about them as though they're quasi-groups, like I indicated before. You can think of them as algebraic structures. And there's a notion of homomorphism for algebraic structures like quasi-groups that is similar to what you might have seen for groups or rings or other things. And so using that notion, we have what's called a category, which is basically consists of all of these different Latin squares or quasi-groups that I can make, and there's like all of these arrows connecting them, which are these different homomorphisms that transform them into each other in some way. Maybe I'll just leave it at that. So there's a similar kind of world going on for these things over here, because I can also define a notion of like homomorphism for collections of matrices that satisfy this condition. But that notion of homomorphism would basically be saying, well, if you let me think of relabeling by saying that like this is row 1, or this is column 1, column 2, column 3, row 1, row 2, row 3, and then like this is matrix 1, this is matrix 2, this is matrix 3, then, well, if you allow me to define, there's like an analogous notion of homomorphism for these things that has to do with relabeling the rows and like reorganizing the rows and the columns and the matrices. And I'm not going to try to sit here and write it down right now, but there's an analogous definition of homomorphism for this data. And according to that definition that I have in mind, the category of quasi-groups or of Latin squares is isomorphic in the indicated manner to the category of these things. And so in that sense, those concepts are the same concept. And like this is a general theme whenever you have two different ways of expressing the same data and no other concerns in mind, you can always kind of view them as just, giving you isomorphic categories, which from a category theory perspective, people would usually say is not very exciting. But usually equivalence is more exciting than isomorphism. But let's see. So Okay, I guess. Okay, well, since we have a question, I'll say a little bit more. So, um, so, uh, so the idea would be that there are. So the idea would be that there are two. So there are two like worlds. So there's I guess I'll say Latin square world. And so inside of here there are like little like Latin squares, like 1 2 2 1, 1 2 3 3 1 2, 2 3 1, and maybe 2 1 1 2 or whatever. And there are a bunch of different arrows that are these morphisms going between them. And maybe there's some other ones like that are like this, like this. There are all of these various homomorphisms. And then over here, there is that matrix. I'll just call it matrix tuple world. And there's matrix tuple world, and matrix tuple world has things like 1 0 0 1, 0 1 1 0. And by matrix tuple world, I mean that the things in here are like the lists of permutation matrices that add up to be, they have the correct number and add up to be the n by n permutation matrix. So like 2 2 by 2 matrices, 3 3 by 3 matrices. Maybe I'll just right. So there are a bunch of things like this, and like the one that corresponds to 2 1 1 2 would be like just 0 1 1 0 1 0 0 1. And just like before, these have different, you could define something that would be like a morphism between these that would be analogous to the morphism between Latin squares. And so now the claim that they're isomorphic is that there's a pair of functors, and a functor is something like this. Maybe I'll call it big F. And we would say, like, if you took big F and you plugged in the Latin square 1 2 2 1, you would get the thing over here, the object over here, which is 1 0 0 1 0 1 1 0. And yeah, and I would have to also, if I was actually doing this in detail, then I would also have to tell you if you have a homomorphism of quasi-groups over here, I would have to also tell you what the meaning of what the meaning of FH was, and it would have to be a homomorphism of these things over here, and there's some other conditions that have to be satisfied, but the claim is basically that you can, once you know that the data of these guys corresponds to the data of the Latin squares, you can just basically lazily steal the structure of this category and just re-express everything in terms of the lists of permutations instead. And those two things are... Oh, okay. I guess now that I'm thinking about it, I suppose I shouldn't have said isomorphic, because, let me... No. Okay. It depends on what I mean, actually. So if by Latin squares I mean that they have to have the symbols like 1, 2, 3, and so forth as their set of symbols that they can be on, then these two things would be isomorphic. However, these two categories would be isomorphic. I mean, there would be like an inverse functor, big F inverse, that goes back the other way. However, if I allowed my Latin squares to actually be quasi-groups in the sense that they can have different underlying sets, then maybe I can have an order 2 Latin square or quasi-group whose basic symbols are like 3 and 5 instead, and then this would be a different thing, and now maybe big F would send it to the same thing as 1 2 2 1, for instance. And so if I include this in what I consider to be my category of Latin squares, then I guess I would only have an equivalence and not an isomorphism, but okay, maybe let's just not worry about that right now. Unless everyone's very curious about it. It's getting a little far afield from the combinatorics that I was going to try to do. I don't know. What does everyone think? How are we feeling about this? All right. Well, yeah. So these have the same data, and Okay, well, just let me know if you have other questions, but I'll remind us again. So, oh, I'm not sure what the what was fully faithful. Okay, well, let me know let me know what you were. Oh, are you just saying like an equivalence of what like what's going on with an equivalence of categories? Yeah, it's you're probably thinking like, two categories are going to be equivalent when or you'll have an equivalence when you have a functor that sends one category to the. Oh, so yeah, okay, so I guess I'll just briefly comment. So what I was just saying was that there is an isomorphism between, so originally, like with this setup where you're only allowed the symbols 1, 2, 3, whatever, and in your order n quasi-group or Latin square, whatever. So what I was talking about was an isomorphism of categories, and so that would be like if I call this category C and this category D, that would be like saying that there's a functor that takes C to D. It's like what a homomorphism is for categories from C to D. And then there's also another functor that I'll call F inverse. That's suggestively called F inverse from D to C, and it has the property that if I do F and then F inverse, I get the same thing as the identity functor for C. And if I do F inverse and then I do F, then I get the identity functor for D. And so that's what I mean by an isomorphism of categories. So it's basically like it's actually like isomorphism for Latin squares or for quasi-groups or magmas or whatever, but it's for categories instead. Categories are some kind of similar, maybe more complicated in some sense, but some kind of similar algebraic gizmo, and there's a notion of isomorphism for them as well. And maybe at the beginning it doesn't seem like quite as clear that this is actually the same kind of idea, but it is. It pretty much is. It's just got some more bells and whistles. Yeah. Now confusingly, and I won't get into this other than to make the comment, two functors can also be isomorphic to each other. In some other context that I won't give right now, but so yeah, you actually have to be careful for when you're saying, is this functor an isomorphism, or are these two different functors isomorphic to each other, and those each mean a different thing. Yeah. So maybe I'll leave it at that for now. Okay, so these Sij's were supposed to be the bad tuples of permutations. So remember, we have a list of distinct permutations, and this was supposed to be the situation where we have a list of distinct permutations, but the IJ spot in each of them are all the same. Thanks to algebraic geometry for making us think about things like when two functors are isomorphic versus when one of them is an isomorphism. Because if that's what you're saying, then I'd have to say that, well, a lot of this stuff also originally came up in the context of algebraic topology, and it for people doing algebra especially, but even other areas, like it was basically inevitable that this kind of thinking would arise, I think. Yeah, I guess Grothendieck's initials are also the initials of algebraic geometry. yeah. He definitely latched onto these. I mean, in addition to also propagating quite a few of them himself. He really latched onto this stuff pretty hard. So, yeah, yeah. Thanks. But yeah, I do think it really is quite quite natural. Um, you know, since natural has a technical meaning in this context as well. It's quite natural to consider a lot of these things. Um, yeah, so these SIJs were the bad. They were the bad lists of matrices that didn't fill in one of the spots. And I think I had an example up here actually. Yeah, so for the n equals 3 case, if you have these three permutation matrices, which are three different permutation matrices, then they're in S11 because this list is in S11 because if we look in the 1-1 spot, there's not a single thing that gets put into it. So that's bad. In other words, we have a question mark here. We don't know what to put here. On the other hand, they're also in S3 too, because so if we look at the third row and second column, we don't know what gets put here either. It's a big question mark. Now, I wouldn't worry too much if you see over here we had a comment about these things that I called TIJs. We had just had a conversation last week about like, well, what if you defined it basically in terms of like when there's more than one thing stuck into an entry at the same time. And I said, yeah, you could probably actually formulate this in terms of that as well. I'm not going to do it that way. I'm just going to follow what's in the paper, but like, there's another perspective as well. Because notice, if you don't put anything into this spot, then that means that there's going to be too many things over in this spot because you have to, you have to choose to put the one in the first row somewhere, the one in the first row here somewhere, the one in the first row here somewhere, and if you don't use this spot for any of them, somebody's going to bump into somebody else. It's the pigeonhole principle, right? If you've got n+1 pigeons and only n holes, 2 of the pigeons are going to have to live in the same hole. And I'm not really entirely sure where this came from, because who thinks about pigeons living in holes? Oh, I realize now. Actually, pigeons are sad. So, people used to both use pigeons to like deliver messages, but they also used to keep pigeons as pets and breed them to have like those pretty colors that you might notice sometimes. And then when they became less useful to society because of the mail delivery thing not being so necessary, people just stopped taking care of pigeons for the most part. And now pigeons are just like these wild animals that live in cities, and people call them like flying rats and stuff, and are like very like dismissive of them. But like pigeons were our pets, and we like abandoned them. It's actually pretty sad. So I bet that mathematicians before used to actually have pigeons, or at least know someone who had pigeons, and their pigeons would probably slept in little pigeonholes or something. Okay, I like this now. Actually, I think this is a good thing. All right. Anyway, that's my story about pigeons. So if you see a pigeon out there in the world, try to be nice to it. They've had a hard time. We've let them down, honestly. All right. Well, anyway, so now in order to explain where this formula came from, I wanted to explain the inclusion-exclusion principle, which is an important thing in combinatorics. And so just to remind you that the idea was, if you want to count everything that, like, I think I gave the example before, it was like, there's some students in a school, and some of them are taking class A, and some of them are taking class B, and if we only know that like 30 students are taking class A, and 20 students are taking class B, then we don't know how many students there are overall. There could be 50 if, say, A and B took place at the same time, and you couldn't take both of the classes at once, but it could be that they don't take place at the same time, and maybe 20 people are taking A by itself, 10 people are taking B, but 10 are taking both A and B. So you can't just figure out the size of A union B by adding up their sizes. You've got to also subtract the size of the intersection, because the intersection gets double counted when you add up the size of everybody taking class A and everybody taking class B. So then you can get the correct number. And then the thing was, and I'll go through this a little bit faster than I did before, but just ask me if you're curious about something or you want more detail. When you do it for 3 sets, when you add up the sizes of all of them, now these aren't indicating the numbers of things in each of these sections, they're indicating how many times they get counted. Well, we'll count each of the things that are only in A once, but if we add up the size of each of these 3 sets, we'll count the things that are in A and B, but not in C, twice, and we'll count the things that are in A, B, and C 3 times, because we'll count once for A, once for B, and once for C. Okay, so that's not the right number. So then we try the same trick and subtract the size of all the intersections, but when we do that, we actually take away the stuff that's in A intersect B intersect C 3 times, and so there's none of it left, so this number is too small. But then if we add in the size of A intersect B intersect C, we fix it, and we count each of the things exactly as many times as we should. And this trick works in general, and that's actually pretty much where this expression is coming from. Let's see, here, where we have -1 to the size of the set times the size of this set Sx. The one thing which I stumbled over a little bit before but ended up realizing what I wanted was that they're being a little bit sneaky in how they're setting this up, and they're doing it in a way that includes the possibility. Oh, hey, yeah, actually, it's just happened that other things that I've been doing, you know, just for different live streams have been maybe less. If they've been combinatorial, they've been less, like, you know, explicitly, like, you know, enumerative or whatever, but I do this type of thing. Actually, even when I talked about the rock, paper, scissors project that I had before, if you go and look at that paper, I do actually, you know, they're maybe not, I guess I wouldn't say they're the most involved counting arguments, but they are, I do give count, you know, I do give a lot of quantities of things in that paper as well. Or even like the earlier this summer, I was looking at sizes of minimal triangulations of you know, of manifolds, compact orientable manifolds, and, you know, there was some counting that some other people had done going on there. So yeah, I mean, I like combinatorics, not just the, you know, simplicial complex kind of, you know, topological sort of things. I do like good old-fashioned, you know, combinatorics as well, inclusion, exclusion, and all of this sort of thing, finding bijections. But yeah, so you know, because it's, I mean, I do have a few areas that okay, no counting for you, huh? Well, you know, if it stresses you out, you know, counting things is just figuring out the, you know, I mean, numbers are just, you know, they're just certain kinds of topological spaces or homotopy, you know, types of spaces or whatever. Let's see, I don't, I actually, let's see, yeah, let's see, flag transitive homogeneous simplicial complexes. Okay, so let's see. So I have. So you're saying I have an action on a simplicial complex that's transitive on flags, and I take it that given the context, it sounds like this is supposed to end up collapsing to just a discrete set of points. Is that the idea here? Let's see. Or is it like up to actually, wait. Okay, that is the idea. Okay, now I'm curious. Okay, so now, okay, I'm curious enough. I want a little bit of an aside. So, okay, so if I have this, let me see. Okay, so so flag transitive should mean that they're, so okay, well, okay, so like one flag would be like this vertex, like I have like A, and then I have A sits inside of AB, so that's a flag, and so there should be a map taking me to any other one. So like there should be a map taking me to AC or AAC, and similarly, does homogeneous what is homogeneous to you? Is it that everything is contained in a maximal in a facet of the same size, the same dimension, or I feel like okay, and so the transitive is that there's the automorphism group acts transitively on flags. That's the group that's acting on it, is the automorphism group of the simplicial complex. Oh, okay. So I see. So I'm thinking that I'm correct. Yeah, okay. So this is bad. Okay, so this is bad because I can take AAB to AAC, but if I have AB and AD, then an automorphism should not be exchanging these guys with each other, because if I remove AD, I get a 4 cycle, but if I remove AB or AC, I end up with yeah, okay, I see. So okay, so this isn't flag transitive. All right, I guess I'll buy it. I'm not gonna sit here for long enough to actually see the whole thing. But I am gonna be honest. It's not instantaneous to me, and I haven't heard this joke before. But I see. Okay, so I can't have that because that wouldn't be flag transitive. So okay, I will buy this, but I will fully admit though that I don't think I've ever seen this comment before, and it wasn't immediately obvious to me. But okay, at least I was able to reproduce the the correct definition and see that this example doesn't work. So that was something. It's funny, honestly. So I definitely feel a lot less shy about just messing around on live stream than I used to when I hadn't done this yet. But still, it's like, I do things like this, and then I think, to someone who wasn't in any area related to this at all, it probably is like, oh, that was like very quick to like get what that person was talking about. You looked at the example, whatever. I mean, I didn't, do the whole thing, but like I at least started to look at it. And but like I did this, and then I was like, should I be embarrassed that I wasn't instantaneously producing the entire demonstration, like having never seen or thought about this before that I can recall. I guess the answer is probably no, like, but we all feel like this sometimes, don't we, Okay. Yeah, I think this is just a thing that I haven't, this is just a particular thing that I haven't happened to look at as much. I have seen like, in grad school, I saw some amount of, group actions on graphs, in various classes of graphs like this, but I don't spend a lot of time thinking about like just general classes of graphs like this. So I do like combinatorics, but like this exact thing I don't think about too much. So if that's supposed to be a hint to how to show that it has to be a discrete space up to homotopy, I still don't have it. But yeah, thanks. That's a cool thing. Yeah. So okay, so now that humorous comment has been beaten to death, okay, so where was I at here? Oh, so I was using inclusion exclusion, and so if you'll remember, there was this other like little like there's this other like little caveat, which was that we were using inclusion exclusion here, but if you look carefully, the size of sets that had wait, wasn't your comment part of the like the humorous thing of like, you know, we want to find like a different way of describing discrete spaces, or just, you know, discrete spaces up to homotopy, you know, that isn't just, you know, saying they're like finite sets or like numbers, you know. No, that wasn't the conversation that you were part of. Okay, but you did say yes. Okay, I'm a little confused now, but you did say yes to me saying this is supposed to be something that has the homotopy type of just a discrete set of points, right? Okay, I'm not 100% sure, but I thought we were finding unnecessarily convoluted ways to talk about what numbers or finite sets were. You know, for those who have for those who are uncomfortable with numbers or with counting, is that not what we were doing? Oh, okay, but was. Oh, okay, I see. Yeah, because I said I like simplicial complexes. But were you saying yes to when I was saying, oh, is that supposed to just have the homotopy type of a discrete set of points, or are they more interesting than that? And by they, I mean the flag transitive homogeneous simplicial complexes. No, they're not. Okay. Oh, okay. Sorry. Well, of course I couldn't find a proof or see the argument because it's not true. Okay. Now, okay, even though it's an aside that came from a confusion, I think we just got our wires crossed a little bit. Well, this isn't an example of one, but that means I probably should be able to come up with an example of they can have non-trivial homotopy, right? Because if I take this, then okay, then it's the symmetric group on 3 letters, and I can take any flag to any other flag, and everything is, and this is I guess what you call homogeneous, I think I would call pure. Like every simplex, like every face of this thing is contained in a maximal one that has the same dimension, the same size. So this is actually an example with non-trivial homotopy, right? Like this is the circle up to homotopy, or even homeomorphism, I guess. This is the type of space you're talking about, right? So like this thing over here is a non-example because it's not flag transitive, but this thing is flag transitive, and it's what I would call pure. Is this what you meant? Yes. Okay. All right. Sorry, we just got our wires crossed a little bit. You happened to mention those right when I was saying something about like, oh well, you know, like, you know, if you know, if you don't like that, just think about the homotopy. You know, if you don't like counting, just think of the homotopy type of, you know, spaces that are homotopy equivalent to just a discrete space, you know, compact discrete space or something like that, you know, and so you just happened to mention those at that time. But now I see when I thought that you were saying that those had to be discrete up to homotopy, then I was like trying to figure out how to prove it. But as soon as you said no, you know, we were confused, and you know, I was confused at least, and they can be non-trivial, then immediately I produce a non-trivial one, which really goes to show that if you tell someone they can do something, it often makes them able to do it. Okay, well, good. I'm glad that I wasn't able to prove they were all trivial. If I was able to prove they were all trivial, that would be much more embarrassing than just having not noticed the triangle before. But okay, that's life. Okay. So yeah, I mean, I like these guys just fine. I don't know much about them yet, but they seem good. They've got the triangle. I mean, that's a solid start. They have the they have the circle. Seems good. Yeah. Okay, so so we had these sets S, I, J. And then those are the ones that were bad in that coordinate. And then we have these sets Sx, where x can be a set of coordinates, and these so this Sx for this x would be all of the tuples of permutation matrices that are bad in coordinate 1, 1 and coordinate 2, 2. And so this is why the idea is that we can use inclusion exclusion, because if we think about the formula that I had up here, this is only for 3 sets, but the same type of thing works for bigger collections of sets. We have to know the sizes of all of the big sets, and then their pairwise intersections, and then their triple-wise intersections, and so on and so forth. And that's exactly what these sets Sx are, with an important additional consideration that caused me to trip up a little bit last time, but that I understood before the time was up. And that is that if we take x to be the empty set of coordinates, that will just be, well, it's the things that are in the Sij, the intersection of the Sij where I and j belong to the set of coordinates. And so if the set of coordinates is empty, that's the empty intersection, which is like the ambient world of all of the possible tuples of distinct permutations. So that's a little bit of a corner case. And it's also similar to the comment that was made before about how when, remember back up here where we said, the terms don't really show up unless the permanent is at least the size of the matrices, but they just include in the formula just per A choose n, even though for a bunch of these matrices in Bn this will be 0 and that whole term will be on. There's the same type of sneakiness happening here where they just say we'll use inclusion exclusion, but then what they actually do is they figure out the size of the number of these things, because they say, okay, the number of n by n Latin squares is the total number of these distinct tuples of distinct permutations minus the bad tuples of distinct permutations. The bad tuples of distinct permutations would be the union of all of the Sij for different i's and j's, right? And so that would also be like the size of all of those lists of permutations minus the union for which over the x's that are not 0 of these s sub x's, like the example I gave up here. But then this set S, that's the whole thing, all of the possible tuples of distinct permutations of size n. This is like S sub empty set, right? That's like when X is the empty set. And so by inclusion exclusion, we have that if we sum over the x's that are not the empty set, we'll do -1 to the size of x minus 1. If you go back to our example from when we were doing this, you'll see that the reason for that is that when we're at the first level and just taking the original set, in our example we have one coordinate. We have exactly one coordinate that we're thinking of as being the bad coordinate, but we shouldn't get -1 to the first power, because that would be a minus sign here. We want -1 to the 0 or 2 power, whatever. We want an even power so that we get plus signs like we're supposed to. Okay, so that's it's math. It's happening. I know, I expressed so much interest in category theory and topology and stuff that you might have worried that I wouldn't actually be computing things, but don't worry, I will. and even when I do those more abstract, perhaps, depending on your perspective, abstract things, I usually do always try to make sure to reach actual calculations in the end too. Even in, the most abstract things that I do, there are also, there are concrete calculations that come up. It's if you like the concrete calculations, the perspective is that you actually need the abstract stuff to help you get to more interesting and fun concrete calculations, and that's the role that it has for you. Oh yeah, it looks like I will need to banish someone who's spamming me here. So let me do that. Just a minute. And yeah, I'm glad that the category theory stuff helped you to find a cool rabbit hole on Wikipedia, and that was a good thing to be doing. Let's see if I can find the moderation stuff to be doing here. Let's see. Yeah, it's funny actually. The first example of a bot that was suggested when I was like, okay, I need to report this as a bot. The first example was actually what was I gonna say? The first example was the type of bot that it was. It was like one of these like viewer bots. Now my next question is, how do I actually? Let's see. Not sure if I can actually erase a message from the chat in here, but that's okay. We'll just have to live with it. All right. Well, because I'm lazy, I can't just eliminate the spam. But since this one isn't really offensive and it's just some spam, which I've actually never gotten before, incredibly enough. I mean, I've gotten the offensive stuff before, not the spam. Oh yeah, I reported them, but I didn't ban them. Let me try that. Thank you. So let's see. So yeah, I guess you can just report someone, but you can't ban them. But it doesn't ban them automatically. Let's see. I don't think it did it automatically, but that's okay. I don't really want to exit the chat and then re-enter, so I'll just let it go. I'm not sure I really understand the comment here. I feel like this is a joke, but it's just some spam until you have overdraft on your bank. I'm not sure I get this one. Let's see. Okay. Yeah, I'm sorry. I just didn't understand. I didn't understand that joke. I assume it had something to do with the business of cultivating these follower bots and stuff. But I just don't. I'm not entirely sure. Sorry. Okay. I'm just gonna get back to it. Hey, who knows? Maybe if that virus link or whatever it is still active when I post this on YouTube, you can try checking it out then too, and just let me know if if you get infected with something in your machine or whatever. All right. Well. Anyway, so if you'll remember, I was saying, okay, if we do inclusion exclusion, I have to put this -1 there because it makes all the minus signs come out correctly. Is basically the point. And then when I do the subtraction, it has the same effect actually. It's just summing over all possible sets of bad indices x, including the empty set, and this minus sign and this -1 power actually cancel each other out to give us this formula, which is the formula that's in the paper. And so this means that we can actually reduce the entire problem if we've all followed through all of that. We can reduce the entire problem of counting how many Latin squares there are to counting how many of, or counting the size of these sets Sx. And so, of course, it's possible that it's not easy to count those either, but the claim is that we can do it. So, well, let's try to do it. Of course, this one we can be quite confident about because it's in the paper. But the question of whether it can be generalized, I'll address shortly. So, okay, so now they're just kind of repeating different things that they've said so far, or, you know, saying they're combining things, whatever. I read the paper in some other order. So the claim is that this Sx is the set of n permutations of the elements in Px. So what is this Px? Oh, I should really read the things that come before. So this Px would be all of the n by n permutation matrices, which are contained in this A of x. Okay. Oh, this wasn't discussing. It's easy. I skipped past this because I thought it looked very similar to something else that I had seen before, and then I realized now I needed it. All right. Well, let's actually take a look at this. We need the formula for Sx. So A of x is the 0, 1 matrix of order n with zeros in the positions of x and ones in the positions not in x. Okay. So in other words, yeah, I mean, it's just saying that, like, in our example, if you'll remember, we had our example up here where x was 1, 1 and 2, 1. That our A of x here would be the 2 by 2 matrix whose entries were in whose ones were in positions 1, 1 and 2, 1. So that would be A of x. And let's see. So, well, okay. So if we have a list of things that are bad in the positions in x, whatever those are. So we have a tuple of permutations that are bad in those positions. That means that well, that's the definition, and so that would be the same thing as having this, and well, yeah, that would be like saying each of these guys is less than or equal to A of x, where less than or equal means like in each coordinate simultaneously. So for instance, what could be in S11, S21? Well, okay. Actually, this one's a bad example because it's impossible. Yeah. So this one's actually not a good example. So we need a slightly larger example in order for this to be possible. So yeah, for 2 by 2s this doesn't really come up as much, but I had a bigger example here that I can look to. Okay, so like, let's see. Oh, yeah, because I need a bad example that is okay. Yeah, I'll produce a bad example. Oh yeah. Yes, I said in the stream last time, I wish that they had just said it's the size of S minus the bad ones, even if they collapsed it into like a single formula after that, just making the comment, because when you see it and then you're like, okay, it's inclusion, exclusion, and then you're like, wait, like this doesn't, it's not exactly that, then like there's like a little bit of a hiccup, but yeah, it didn't take me that long to figure it out, but it's just a nice thing to say, and I mean, why not? It's not like we actually have to use paper to print these things anymore, right? Okay, it still costs some electricity and stuff, but it's not as expensive as the paper, I'm pretty sure. Yeah. So, okay, so I need to produce so my goal, I'm going to actually base my example on this. My goal is to produce a bad tuple for the n equals 3 case and show you an example of this. So So let's consider a bad tuple, which is say this one. So this is going to be a list of distinct permutation matrices that can't be that can't correspond to a Latin square, right? So, okay, you already know that this isn't going to work because there's a 1 here and there's a 1 here, and that's impossible. So let's see. So then I have to choose one more. I already know that it's bad. I just have to choose one more distinct permutation from this. And you know what? Why don't I just choose this one? Why not? After all, why shouldn't I? Okay. So all right. So if we look at this thing, so this actually belongs to Sx, where the set x of coordinates is, let's say, 1, 2, 1, 3. Yeah, let's say 1, 2, 1, 3, 3, 1. Okay. So then if we go back here, so A of x would be the 0, 1 matrix where zeros are in the positions of x and ones are in the positions not in x. So that would mean we'd have zeros at 1, 2, 1, 3, and 3, 1, and ones everywhere else. Like this. Okay. And so then if you take any of these matrices here, you'll see that this matrix that I gave here, this is my A of x, this is greater than or equal to any one of these matrices. Like for instance, it's greater than or equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. And that just means if you look at any one of the entries, or I'll make a nicer looking one here. Look at any one of the entries in these two matrices, look at corresponding entries, like here's a 1 and here's a 1, that's greater than or equal to. Here's a 1, here's a 0, that's greater than or equal to, 1's greater than or equal to 0, and so forth. So like each of these three matrices is inside of this A of x. So that's what they're saying. Okay. So well, let's see. Why do we care about that? Well, if we consider the set of all n by n permutation matrices contained in A of x, well, the number of those is this permanent of A of x. I actually made this comment before, not having actually read this thoroughly. Remember, well, if you were with us last time, I made exactly this comment, and I actually literally said, without having, I've never really thoroughly read this before now. I've just skimmed over it, and you could tell also because I didn't realize that I needed to actually read it just a few minutes ago. So I previously made this comment that the permanent was all of the n by n permutation matrices contained in a matrix, and they're actually using that now with that exact language. All right, but the question is always why should I care, right? Why does this matter to me? I mean, you can just like it. You're allowed to just like anything you want to, but we have a goal here. We have aspirations and stuff, right? So like we should be motivated by that. So okay, well, the claim is that this set Sx, which remember are all the tuples that are bad in each of the positions in the set X, this is actually n factorial. The size of this is n factorial times the size of px choose n, which is the same as n factorial times the permanent of A of x choose n. All right. Well, why do I care about that? Again, well, okay, let's think. So if I have something that's bad in each of the coordinates in x, then that would mean that I had chosen I have chosen a list of n distinct matrices that are bad in each of those coordinates. So any matrix that is or well, let me say it this way. Being bad in those coordinates, as we saw here, is equivalent to each of those matrices being less than or equal to A of x. Right? And so we might as well say, well, you're going to choose n different matrices that are less than or equal to A of x. You're going to choose n different matrices less than or equal to A of x. And, well, we have to give some kind of ordering to them, right? Because, we're supposed to be making a tuple out of them, but we need them to be distinct. So we choose n distinct ones, but that's an unordered choice. And then we put the ordering back in by saying, there's n factorial ways of putting them into an order, and each one of them will give us a different possible bad tuple, and that's what all the bad tuples look like. I see. And so, okay, but the size of that set is the permanent of the matrix A of x, and the matrix A of x will be like the matrix A for some choice of coordinates. That's why it's this. Yeah, replacing A of x by A, because A of x, that will be some, at each 0, 1 matrix will be A of x for some choice of x. I see. Okay. So, all right. Well, I mean, honestly, that's pretty much it. I don't think I have a lot more to write about just understanding that. Does anyone have any questions or want me to do something in more detail? I actually feel good about the remainder of that that discussion now, since I wrote down the example. Okay. And in case you're wondering about bots, the Ko-Fi bot is mine. I debated setting it to go off at larger intervals or just to turn it off entirely once I realized that, it's probably overkill. I did actually make a good amount of money doing this at the beginning when I really needed to, because I was struggling more. I still am definitely not out of the woods financially, but I'm supposed to get paid for the first time by Boulder this week, so hopefully things will be fine. And I did make it through the summer, but it's I just realized it's just more effort than it's worth, and it can't hurt to just remind people, if you can, help support. But another great way that you can support me doing this career and being myself and everything is just by hanging out and chatting in the chat and just saying hi, or watching on YouTube, or maybe somewhere else if I ever post anywhere else. All right. Well, anyway, that's probably enough about that. So writing down this example is really very helpful to me. So I feel like this is too easy. I feel like the higher dimensional version of this it feels like it's got to be too easy, right? So let's try to actually think about that, assuming that there are no questions or comments or anything. Well, let's see. So I already claimed. Oh, yeah. Well, I'm glad that I can be one person doing it. To be honest, as I think I've mentioned before, I have heard of there's definitely other people who do some kind of math related live stream or who make YouTube videos or whatever. Actually, I think there's even I was checking out everyone's website. Okay, maybe not everyone, but just I was poking around on people's websites and stuff for the new department I'm in, as one does. I always think I'm going to check out everybody's stuff, but I never have the wherewithal. But there's various people even at Boulder, I think, who have some kind of web presence like this. I don't think mine is super huge or anything, but I'm glad that people are interested in checking it out, and it's I think it's a good thing to do. I feel like it's actually been really helpful for me as well, because I just I feel like, when I'm teaching, like I'm sharing, I'm sharing things that are a little bit more prepared, and then I do stuff like this more with like students who I'm actually working on like research projects with, or that type of thing, where it's more, it's a little bit more on me because I'm I'm the professor and everything, but I feel like this just fills a good niche where like I don't feel like as much pressure to like produce quickly when I'm doing this because I'm trying to be more expository, but I'm still doing something that's like, hopefully not trivial and is educational, and like, I feel like it's got a good it's in a good place. Like I wouldn't want to sit here and literally talk to myself for 3 hours every week and do the same kind of thing, but even just having a few people who show up each time and a few more people who check it out on YouTube it's really rewarding. Oh, well, I mean, I think I saw in the YouTube comments for the first video I posted back when I was still using my old like undergrad YouTube account that got like a lot of views. That was like 50,000. Somebody said that they had done like some of their master's thesis stuff or something in a similar way, but then they stopped doing it. I'm just saying I'm not 100% sure that I'm the first, but yeah, it's I definitely, there's not a lot of people doing this type of thing at the moment, but yeah. If the structure of all the publishing and stuff was totally different and it wasn't any concern, like honestly, even if we had like universal basic income or something and I literally didn't have to have a job and I could just sit around and not worry about like someone scooping me to like get a good paper so that maybe they get tenure and I don't get tenure and like all this type of thing. Like if none of that mattered and I didn't need to make like $1 bajillion, I actually got enough money to just live, I would probably just be happy to just hang out and like, like maybe I wouldn't want to do everything totally live because like, for instance, if there was like a cool project that I was working on people with, it might be stressful if people were always coming and going like at all times and there was like a crowd of like 40 people watching us while like only like 5 to 10 of us did stuff together at once, but like, so like that could be a little bit stressful, but especially for stuff like this where I'm just like trying out something myself and like, it's not necessarily expected that the audience like gets like fully into it to the level that we're like doing, we're doing it together in that sense. Like, I think that I would write papers like this. Like I would literally just sit here and like write papers like that. I'd be like, yeah, I'm still working on my paper and like, let me show you what I have going on. And, well, anyway, it can't be, but finding a generalization of this formula isn't something I would probably publish anyway. So, it's, yeah. I don't know. It's a weird time. I don't want to rant too much. You'll probably get bored of me, imagining about the future or whatever. But I do wish that I didn't have to worry about this type of thing quite as much, because it's just, to me, it's not a fun part of doing the job. Having to manage like when people know what is like some like social thing that I don't want to deal with. It's not a fun part of socializing to me. It's a tedious, a tedious thing to have to keep track of. Anyway, okay, that's enough of that. Yeah, I hope in the future I can just say, oh yeah, like look, I see. I know why I'm not entirely a fan of. It's got to be this in order to write a paper. It can't just be this, because if it's just this, what'll happen is there's people who will record themselves for like hours and say, look, I proved this theorem. I proved it on the stream. And then if you try to, say, like if you try to investigate this and you say like, yeah, I've written down the proof of this, I've proven this. As long as the current publishing system still exists, then that other person might say, you can't do that because I clearly proved it first because I proved it on the stream. Even if there's like gaps or like you don't feel like that was really a complete proof, it becomes like this very like vague thing of like what is a legitimate complete proof that was already given on YouTube or whatever, right, on Twitch. And that's not good for those of us who actually really do need to make money from doing this. Because those of us who don't can just blow over the other ones by like just half proving things and then saying that they get the credit for it, so you can't publish on it, and they don't need to publish because they have money, and that could be bad. Yeah, but if money was no object at all for any of us, then who cares if somebody kind of proved it on their stream? Nobody would really care quite as much, probably, who was the first person to do whatever. It would just turn into who is the most fun person to do math with. And that's also kind of a social thing, but that's a less stressful social thing if money's not a factor. Anyway, okay, I'm done ranting about that. I hope that was somewhat interesting. All right, well, so I feel confident that I can describe the higher dimensional version of this thing now. First, I have to tell you what I mean by a higher dimensional Latin square, right? So, for us, let's see. Is it a good thing to say in a statement of purpose on a grad app? Like, I know I will not get tenured, so I rather teach, but if I can, I'll do research. I don't know. Like, okay, here's what I'll say about whether it's statement of purpose for grad school or just applying for jobs or whatever. The reality is that, like, so you're a human being, you're a young person, even younger than I am probably, who exists, you know, and you maybe have a presence on social media, maybe even more than I have, you know, like, you have opinions, you have politics, like these are things that exist. Whether you're applying for a job working for the state, as I am now an employee of the state of Colorado, or you're working for a private company, which, you know, private school, which is, you know, a non-for-profit usually in the U.S. that is heavily funded by the government also, you know, you have, you know, you're going to have your own personal politics, but I would try not to bring, I would try not to bring it too much into the application, right? So, like, the reality is, like, I'm recording this, I'm going to post this on YouTube. Until YouTube collapses due to whatever, you know, government stuff or just under its own, you know, weight or whatever, this will probably be available to watch, right? So, like, I have opinions on things, you can hear them a little bit. If you bother to check this out, you can hear them. But people generally won't take all the time in the world to, like, get really deep into your web presence, probably, when they're doing hiring. I mean, I haven't done grad school, I haven't gone through approving, you know, like, selecting students who are applying to grad school, and I haven't done the hiring process for professors, even, you know, even postdocs or anything like that, right? Because I'm still a postdoc. But I would say that probably, like, there's going to be different politics among the people in the hiring committee or the grad school committee or whatever, especially because a lot of those people are significantly older than us, and they tend to have different politics even if they seem broadly aligned with you. And so, aside from the fact that someone might disagree with your ideas, there's also just the fact that people will get a little squeamish, I think, if you are too intense about certain things. So, like, I know that this is not a fun thing to hear, but, like, similar to how politicians end up being, like, very wishy-washy and, like, not having a really solid position on anything, I think being a little bit, you know, diplomatic can go a long way in these kinds of situations, because, you know, they're not going to get into all your stuff. So, I mean, it's natural, you're going to have opinions, they're out there somewhere, but, like, if you need to pass through, like, a round of people who are quickly going through all the applications and through all the statements and saying, okay, do I like this person, do I not like this person, you've got to achieve that snap judgment from people who might not agree with your ideas. And so, like, I would say, especially if you're applying for a PhD, right? Like, if your goal is to get a PhD, then, like, you should at least pretend that you're interested in going on to do research. Because, like, okay, forget all the political stuff, right? Like, I mean, that was my opinion on including that in applications. And by political, I really mean, like, the stuff about, like, the structure of the discipline, right? If you have stuff about, like, diversity, equity, inclusion, like, that stuff is not controversial in this sense. There's maybe a little more to be said about it. It's a little more complicated than that, but that's expected. But if you tell the people who you are gonna, who might be your PhD advisor, right? Like that I don't plan on going into academia. They can be okay with you wanting to go into industry or even teaching, but like a lot of people, especially when it's a more competitive environment, are definitely going to be focused on either research, producing students who do research, or producing students who do who go into industry and have a successful industry career. It's not that anyone necessarily has a problem with teaching, but it's just like, you know, if someone's going to advise a PhD that's going to contain original research, I think a lot of people would prefer to invest their energy in someone who's going to continue that, or at least go on to do similar things in industry. Like, I can't speak for everyone, obviously. There are thousands and thousands of people, but I would say, like, so as far as like the opinion about the discipline, or the structure that it should have, unless you know that the department you're applying to is like definitely down with that, and unless you know that you're going to have someone in the department who wants to work with you and who will fight for you to be in grad school, who is cool with you saying, I don't plan on actually having like a research career, I would avoid it. I mean, but that's just my take, right? And my perspective might not be the best, because I mean, well, everyone's got their own perspective, and I'm just one person. But I mean, you know. Oh, I see. So here's the thing. Okay, so you're saying you want to have PhD students? Because if you do, then I don't know if you do, I don't know. I think the only way that you can have PhD students in the United States anyway is if you are I think tenure track is sufficient. If you're a tenure track research professor, as in, I am not sure that the department will support even a tenured teaching professor to have a graduate student, because you know, it's money, right? Sure, that grad student might still be doing the same TA duties that they'd be doing anyway, but it's like part of the the reward, if you want to think of it that way, for having a good research output is to be able to have students, and the department might not want to invest resources in the teaching faculty having students and make that part of the job expectations if you know, I like, again, I'm not 100% sure, you know, I'm only still a postdoc myself, but like, I've never heard of someone having a teaching professor as their PhD advisor, and I think there might be a solid reason for that. And like, honestly, I kind of agree with it, because it's like, why would you try to get tenured as a research professor if you could have mentoring PhD students as part of your job description as a tenured teaching professor? Okay, maybe you wouldn't get paid as much depending on the school, but if you didn't have to have the research output and you just had to produce students, that's way more chill, because students just drop out sometimes, and like, if it doesn't work out, it doesn't work out. It's it's no skin off your back. Oh yeah, well, if your country is not the United States, I can't speak to it very much, so if that's possible for you, that's great. But I think the structure of how the positions in math departments are funded here, it doesn't allow for that. That's why there's so much. That's part of why there's so much competition for these tenured research positions, because people want to have grad students. They want their sort of mathematical legacy to go on in that way, and there's only so many spots. Excuse me. It's time for some water. Okay, so I have a little over an hour remaining in the time that I've allotted for myself. And I was thinking, oh yeah, so I was thinking I'm going to do the higher dimensional version of this. And so, the question is, what is a, well, let's start off with first, what is a 3D, like, Latin cube? Well, the idea would be that it would be like a, it'd be like a cube. Oh, you want me to be your PhD advisor? Well, I won't be advising anyone for at least another year or two probably, because I still don't have a tenure track job. I will probably apply again this year, but I honestly kind of hope that I stay a postdoc for at least 2 or 3 years. I have up to 3 years in my position of Boulder, because I just want to get a lot of good research done, and have a stronger application for a tenure track job. And plus, if I do 3 years here, and then I get a tenure track job, I could still have tenure before I'm 40. I think it's possible anyway, and that's pretty good. But yeah, if you stick around, depending on your timing or how old you are, maybe I could be your PhD advisor. I don't know. Yeah, I hope I'm somebody's advisor. It'd be pretty cool. And just to advertise too, I'm in the topology branch of the family tree. So all of the like algebraic topology people, like Steenrod and so forth. Those are my mathematical ancestors. If you're mathematically descended from me, you'd be cousins with Peter May as well, who it's a well-known topology person. Yeah, it's a good group of people. I mean, I can't mention everyone because there's not enough time, but it's cool. So all right. Well, anyway, what is a 3D Latin cube? Well, okay, I can try to draw the picture, but like it's kind of difficult to draw it well, right? So we can imagine that you can have like this that addition is terrible. Yeah. Yeah, it's actually, the world feels smaller than it really is because so few people do end up going on to academia. You start to like run into people and be like, oh yeah, and then we're like connected this way, and like it's like there's really only so many people, so like it's, yeah. Also, it's been a few generations, so like mathematical, generations in the lineage, so like it's also becomes the thing of like, we're all descended from Leibniz, like some of these really big names. It's like they had lots of students, and then like it's like, yeah, we're all related to that person because like that was the big person who had a lot of students and everything. But yeah, I'm not descended from Peter May. I'm like, or I don't know, like some kind of cousins or something with him. Like we have a recent common ancestor in the family tree. That's what I'm trying to say. Like within the last century, I think. All right. So, okay. So you can imagine taking like a 3D cube and splitting it up into smaller cubes, like a Rubik's cube kind of situation, and then you can imagine like filling in the smaller cubes with entries that have to satisfy the condition that like the symbols in each row, in each column, and each higher dimensional version of a column, all appear once each. But it's a little bit of a mouthful, and it's maybe starting to get a little hard to visualize. So instead, I'm going to give you a better definition of a 3D Latin cube. So I guess I'll just say a Latin cube of I don't know. I'm not sure who that is. But yeah, I mean, you know, even if someone doesn't end up becoming your advisor, it's a very nice thing to say that you would like them to be your advisor, and you know, it also, you know, it can't hurt to send a nice email to someone, just, you know, being reasonable and polite and just saying, you know, you know, I think it would be really cool to work with you. I mean, obviously it depends on your grad school applications and that kind of thing, but you know, it usually, it can't hurt. I mean, people like hearing that. But okay, so a Latin cube of order n. Oh, order n is, I guess I'll just say a set. I guess I'll say theta of tuples. So each of length. Oh no, it's all good. Yeah, there's lots of tangents going on here. Yeah. So that's too bad I'm not doing geometry. So say we have whole tangent spaces here even. Okay, so a Latin cube of order n is a set theta of tuples, each of length 4 for the 3D Latin cube, such that okay, so such that what? If we fix all but one entry of a tuple, say maybe S1, S2, S3, S4. So maybe I'll say tangent space is more wiki time than for category theory. Yeah, there's definitely a lot of different directions that you can go from there. Let's see, S1, S2, S3, S4. Okay, so let's say we fix these, for example, and let this vary. Okay, so if we fix, say, all three of them except for S2, we let S2 vary, then, okay, so yeah, if we fix all but, okay, I'm trying to say this in a different way from the way I usually say it, so let me actually think about this. I want to do this in a better way. I'm trying to do this in a way that's as accessible as possible if you haven't already seen these things before. That's like very down to earth, but this isn't how I usually think of it. How do I want to say this? Okay, well, let me try to actually motivate this without just saying the general definition. So let me take a little bit of an aside. Okay, so remember this example. In this example, we could think about this as actually being a collection of triples, where I could say that I have, like, for instance, 1, 1, 1, 1, 2, 2, 1, 3, 3, not 3, 2, 1, 3. Do people see what I'm doing? See what I'm doing yet? Does anyone know what it's going to be? 2, 2. You see what the next thing is going to be? Or is this still surprising? So like this will be 2, 2, 1. This will be 2, 3, 2. So what I'm doing is I'm saying so here what I'm doing is I'm saying in coordinates 1, 1, so like at position 1, 1, the value that appears is 1. So like at position 2, 3, you know, at position 2, 3 in the table, the value that appears is 2. Okay, so if I go second row, third column, it's a 2. So I can, okay, so I didn't finish, but I can view this as a set of triples for the 2 by 2 Latin square, right? So now instead I want to do the 3D version. So I'm going to think of it as a set of 4 tuples, so lists of length 4, such that if we what? The fact that this has a 1, a 2, and a 3 in the first row is the same thing as saying that if we fix well, it's saying, okay, we're looking at all the things in the first row, so if we fix the first entry to be 1, and then we let the other entries vary, then we're going to get each symbol appearing exactly 1 time, right? So in other words, so I don't want to fix all but 1 entry of a tuple. I want to say if we fix something else, if we fix if we fix let me say it this way, 2 of the first 3 entries of a tuple. So we fix 2 of the first 3 entries of a tuple, and allow the third to vary. The last coordinates will give us each number 1, 2, 3 for n. All right. Well, you know what? I did the mathematician's sin of trying to give you the definition before giving you an example, and then we do that all the time. It's hard to not do it because I already have the example in mind, but I have to let you in on what the example is, and so that's an important thing that I should do. So now that you may or may not, depending on your background, be thoroughly confused. So what am I thinking of? Well, okay. So for a very small example, remember how we had this Latin square, and then we had this Latin square. Think about a little cube where we split it up like this. So it's like a 2 by 2 by 2, you know, it's a 2 by 2 by 2 cube. And make this the bottom of the cube, and make this the top, and make the other one the top of the cube. Right? So this is like the bottom layer, and this is the top layer. And if you notice, well, okay, we have to translate that into the unpleasant definition that I gave before, but that definition would look something like, we have 1, 1, 1, we have 1, oh sorry, I'm missing another coordinate. We have 1, 1, 1, 1, we have 1, 1, 1, 1, 1, how do I do this? 1, 2, 1, 2. I'm thinking of this as like the z-axis. and then I have 2, 1, 1, 2, and then I have, let's see, 2, 2, 1, 1, and then I have 1, 1, 2, 2, and blah, 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 blah. Okay. So now that I've done that, are people starting to feel a little bit better about what I mean? It's like that, like, if you, saying that you fix 2 of these 3 entries is like saying that you're choosing to look at just like a particular one-dimensional like slice of this thing, and then you want to see, like, say, okay, like for instance, say I pick the entry 1, 1, right? That's like picking the first row and the first column, but it's letting the 3D part of it change. And so then I'd see, well, there's a 1 here, and then I look, oh, there's another 1, 1, and if I am allowed to have that third parameter vary, there's a 2 here. Okay, so that's what I mean. I feel like this is actually worse than the more abstract definition that I could have given. This actually isn't very rigorous either. I just didn't want to say that like it determines a bijection or something like that when you project onto the last coordinate, but all right. Well, I have been talking about categories here, so like I'm kind of jumping all over the place in terms of generality. Does anyone want to see a more proper definition of one of these things? Or how are we feeling in general? So basically it's like this. Like I want to have it so that if I look at these rows and columns, or even the 3D versions of rows and columns, I still have the Latin square kind of property. And I can define an n-dimensional version of this as well. So like that's, you know, that's one way of saying it. Yeah, I mean, I think I'll leave it at that. Like there are other definitions. I thought that this would be the most concrete, and since I have a general audience, I thought that this would be the most concrete. But I actually realized I don't like this definition. Okay, but it's fine. Okay, it's serviceable. Okay. All right. So good. All right. So what does that mean for us? Well, if you think about it, then let's see this example I have here, because it's hard for me to draw examples that are much bigger than this. So if you think about this example that I have here, you can actually think about it as being like we could make sort of a 3D matrix that represents where the ones are in this thing, right? And so maybe on the top they're at these positions, and on the bottom they're at these positions. And I'm going to think of this whole thing as like a 3D matrix, or what people sometimes call a hypermatrix. Or even just a matrix when they get sick of saying the word hyper all the time. But this is not your linear algebra, like, two-dimensional matrix, 3D version of a matrix. And, well, similarly, we can also make such a hypermatrix for where all the 2's are. So on the top, oh, I should do it the other way. On the top, they're in these positions. And on the bottom, they're in these positions. And if I add these together, well, perhaps not surprising given that I've been saying I can do this generalization, you get the 2 by 2 by 2 hypermatrix, which is all ones. And so in this context, I'll say that this is some okay, I guess I'll still say P for, I'm going to say permutation hypermatrix, although I have to be careful about what that is exactly. And then here's another one, and then they add up to what I'm going to call J2 here, because it's the 2 by 2 by 2 one, and it's the hypermatrix of all ones. And so it looks like I can do something very similar for these guys as was done in that paper for the Latin squares. And so, okay, so if you believe this, then the question in the remaining hour that we have is, what is an, well, I guess I'll say, I'll just do the three-dimensional one and leave the higher dimensional ones as maybe for next time. So what is a 3D, I'll put in quotes, permutation matrix? What is that? What's the deal with that? What is a 3D permutation matrix? Well, let's think about what we would need in order for it to be the locations of a symbol in a 3D, like Latin cube, right? So it would need to be something where well, first of all, I'm going to say it's a definition, you're fixing any two of the first three positions. Yeah, oh yeah, that's 100% correct, and thank you for joining us. Yes, that is correct. So the reason I was giving that definition, which maybe I should have given I have other much nicer definitions that I can give, but yeah, I was breaking the symmetry on purpose to like help us like psychologically think of the last coordinate as being like the entries that were being put into the little boxes to help with that visualization. But the definition is symmetric in the way that you described. It's not necessary to do that. And actually, you can also, well, anyway, I'm happy to talk about it more if people are interested, but there are several definitions that are similar, but actually the one I gave, I thought it would be the most concrete, and that's why I tried to get myself to produce it, because it was the most similar to what we had already seen. But I think it's actually like the least nice definition to give. So yeah, you're definitely correct though, and just let me know if you want me to talk about the other definitions more, but if you know what these things are, I do also want to try to count them in the time left, so it's up to you. But I mean, well, worst case scenario, I don't finish everything I wanted to talk about today. I'll just talk about it next week. Although eventually I will probably decide I want to do something else, but I'm having fun with this one still. But yeah, that's a great question. Yeah. So yeah, it's true. It's more symmetric than I was indicating before. Okay. So yeah, so what is a 3D permutation matrix? So I'm going to say it's like an n by n by n hypermatrix. And I'll indicate that by saying, well, what should I call my hypermatrix? I'll call it P, I guess, for permutation, I suppose. And so what are the entries of this? What are the entries of this thing? So it's going to be something that has entries that look like P, I, J, K, where I, J, and K all vary over the numbers 1 through n. Right, so it's like an n by n by n hypermatrix that has these entries where if any two of I, J, and K are fixed, there is a unique J so that Pijk is equal to 1, and Pijk Pi I'll say this Pi oh yeah, and how do I want to say this? and so, oh, I said J. I need to say a unique. Okay, if any two of I, J, and K are fixed, then there is a unique choice of the remaining so that there's a unique choice of the remaining coordinate so that Pijk equals 1. All other entries are 0. Okay. So basically this is the definition. This is the definition that I gave before, except now it's saying fix two of the first three coordinates, which are now the I, J, and K for our hypermatrix, which is kind of a reason why I might not want to observe the symmetry that was mentioned before. But so fix three. I guess it's that choosing which is the label and which ones are the coordinates. Like choosing to separate out one of the indices in those four tuples is special. That is the same kind of symmetry breaking as choosing the matrix like this. So choose two of these three coordinates. There's a unique choice of the other coordinate where the 1 appears. And so the effect that this has is it makes it so that in each of these little rows and columns in these submatrices you have exactly 1, 1, but also in like the 3D columns, like if I look, this and this make like a 3D column that's like going up, and there's only 1, 1 in each of those as well. Okay. Do people kind of buy this? That's what I should mean by a 3D hypermatrix. That's a permutation hypermatrix. So if you have any objections, speak now, or I'll go on and say that's what it's supposed to be. All right. So okay. So then my goal is clear at this point, right? I want to say that I'm going to define all of these sets like appear in the paper, where I'm going to say that this set S. So first of all, I'm going to say Sn is my n by n permutation matrices, those hypermatrices. I'm going to say capital S is all of the n permutations of the elements of that, so n tuples of distinct elements of that. And then I'm going to define n cubed subsets of S, which are the ones that are bad in a particular coordinate I, J, K. That's all the same except for adding another coordinate. And of course, Jn will be now the n by n hypermatrix whose elements are all 1, whose entries are all 1. Well, I'm going to do the exact same thing. I'm going to instead say I'm going to choose any subset of positions of n by n hypermatrices, and I'm going to define Sx to be the intersection over all I, J, K that belong to the set X. And please let me know if you'd like me to write down more. I'm just trying to skim through what seems obviously generalizable to me until I reach the hard part, to make sure that I don't want to spend forever writing out the details before I check whether I can actually do the part that seems hard to me. Okay, so now I still believe that the empty set thing works for the inclusion-exclusion. That's going to give us the same kind of formula, but now X is a subset of positions for n by n hypermatrices instead. So again, I need to know the sizes of these sets Sx. And I believe that I can define a hypermatrix A of X for a given set of positions just the same way. And I still believe it's true that saying that I have something that is 0 that is bad in position I, J, K, for all I, J, K in big X is the same thing as saying that each of my P1, P2 through Pn hypermatrices is less than or equal to that A of X. I think that all works the same way in 3D or above. So I need to let P sub X be all of those things less than or equal to that, be the set of n by n permutation matrices contained in that. And now, if I want to define the permanent of a hypermatrix, this is the whole, actually this, honestly, this is the whole trick, right? Because the rest of it is just saying you have a set that contains this many possible choices, choose n distinct ones, you want to give them a different ordering, so there's n factorial ways of giving them a specific ordering. The only question is, can I write down a formula for the permanent of an n by n hypermatrix? And I think the answer is that yes, I can. And I think the rest of this is all exactly what it's supposed to be. Unless I've missed something, I think as long as I can define the permanent in a way that generalizes this statement, then I'm perfect. And actually, there is nothing special about 3D. Then it would work in higher dimensions as well. Can anyone from what I just said see a place where there could be an issue? Because I'm not seeing it yet. I think if I can just write down a formula for the permanent that's the same kind of formula, then that fact is going to be true. What do we think? I know I just went through a bunch of stuff quickly, but I think that's the only part that there's a question. I think this I after sitting here and going through all of this, I think this generalizes directly. I think that I'm seeing this just generalizes to higher dimensions directly. Okay, so the question is, what is the permanent of a what is the permanent of a hypermatrix whose entries are like A, I, J, K? They vary over I, J, and K. I need to define the permanent of this thing. Well, let's remember what the permanent of just a two-dimensional one is. So if it was just IJs, so I know that Rook's, what is it? Okay, wait. Is this the one where it's like how many? So okay, so like rooks will threaten each other if they're on the same row or column, and so there's some question of like, is it like how many rooks can you place or something like that? I feel like I remember seeing something like this before, but I don't remember that much detail about it. I'm not a big chess person. I know there's like chess problems in graph theory, and you don't have to be like a chess person, but I haven't done a ton of those either. The AD plus BC. Oh, yeah. So how many ways can you place non-attacking rooks on a given board? So is it maximal? Wait, I want to answer the rook question first. So is it like how many ways can you have a maximal configuration of non-attacking rooks? Or can I just put one rook on the board and say I'm done? I mean, I guess I'm not going to have, like, I think that, so these are going to be special cases of that. I guess this is what I want to say. If it's what I'm thinking for the rook problem, this will be, okay. So I think you can get stuck, and so, like, even in 2D, I think you can get stuck, right, and not end up with n rooks on an n by n board. But you would get stuck having to have less, I think, I think that's possible. So then these what I'm calling permutation hypermatrices, they would be special cases where you have exactly n of them. You have, or sorry, not n squared in the 3D case. n to the d minus 1 if we're going to do it in higher dimensions, d. So these would be special cases of that, but they wouldn't be all of them. Okay, so yeah, it's probably similar, but I think it's not the same because I think it's just that the permutation matrices themselves, the hyper permutation matrices, whatever, those would be like those special cases of a possible maximal configuration where you have the largest number that is possible, like conceivably, like it would be n squared in the three-dimensional case. But there would probably be other configurations that were maximal, but they didn't have n squared rooks in them, and so it's related, but I think it's not exactly the same. It's not exactly the same counting problem. Because this one way of thinking of it then is like this is like asking something that's more intense, which is when can you have n maximal configurations that are also the best in the sense of each having n squared non-attacking rooks in the 3D version, like the 3D chess version, and they're all compatible with each other in the sense that you can overlap them and they don't have any rooks in the same, no two have any rooks in the same position. It's like asking a more complicated thing, actually, at least on the face of it. But counting the maximal configurations that aren't like the good ones that I'm using here might actually be quite hard itself. So I don't know at the end of the day whether it's really harder or not. But yeah, it's an interesting thing. I mean, I haven't seen the calculation for even the 2D version for that, and I don't think it's what I was thinking of, because I was thinking of a different problem. Sorry. So there was also a question about, have I tried a basis case if the formula works directly, where AD plus B. I guess I'm not sure what you mean by if the formula works directly, or what the matrix multiplication. In the 2D case, the 2x2 board works, right? So when you say 2x2 board, I guess I'm just not really sure. I'm not really sure what you mean by that. Sorry, I think I've just missed something, or I'm not sure what the corresponding thing is. Or what I'm not sure what you're asking is what I'm trying to say. So let's see. So for the permanent in general, and just let me know if you have more detail about the question. I just didn't understand the question. So if I wait, 2 squares by 2 squares for the rook problem. Yeah, I guess I'm just, so like I definitely see that each of my like hyper matrices that I have here, this is like oh, did I drop? I dropped a symbol. This is supposed to be a 1, not a 0. So each of these things, like, so this one is a solution to the three-dimensional non-attacking rooks problem, and so is this one. So any of what I'm calling a 3D hypermatrix will be a solution to the wherever the ones are in the hypermatrix will be where you put the rooks to have non-attacking rooks in higher dimensional chess. But the thing is, there might be examples of a maximal configuration of non-attacking rooks, which are not are not one of these. That seems like it's possible. So I mean, yeah, if that's possible, then okay. But are you saying that Are you saying that every possible maximal configuration of rooks, like in the 2D case? Okay. All right. So, well, okay. I'm just thinking about this now. This is just kind of bothering me a little bit. So, let's see. Like, if I put one here, then I can't have this. Nah. Oh, I see. Yeah. Okay. Right. Because if I put one in any spot, then I will always have. I see. So, okay, in 2D, right? It has to be a permutation. So the number of those. Oh, I see. So the number of those is exactly the permanent. But now in higher dimensions, this is an obstruction to having those numbers be the same. I think that I have an example that you can have a configuration of non-attacking rooks which cannot be extended to like an n by n by n configuration. I think that these are not these things are not the same in higher dimensions. I see in 2D I can just say, okay, I put in this spot so I can choose anything I want out of these two. I fill in this one. It makes that these are forbidden, but then I always have room left. So I can always finish it to size n1. Maximal and size n rooks are the same. But in higher dimensions, I don't think that that's true. I think that it's different in higher dimensions. That there are like partial configurations that can't be completed. Okay, but maybe I will leave it there for now. But I think that that's true. In higher dimensions, it's not the same question anymore. So I really only want what I'm calling like the permutations. And so I think that there are other my claim is that there are other configurations of rooks in dimensions 3 and above that are maximal but that do not have n squared rooks in them in 3D. Okay. Okay, but I don't have to worry about that, I think. Yeah, the YouTube viewers will figure it out. Okay. So well, how does this work? So what I do is I add up a product, say over I equals 1 to n of this ai sigma I, right? And each of these products is going to ask, is that permutation inside of my is that permutation inside of my matrix? So now instead, well, what am I going to end up wanting to do in the end? So I'm going to instead want to say, I'm going to look at things that are a, I, j, I'm going to call it sigma of ij. Yeah. Okay. Yep. I'm pretty sure that this is the. Okay, I'm pretty sure that this is going to be the quantity that I want. Okay, so I and j go from 1 to n, and then I'm going to sum over what? Here, maybe I'll do this over here. Overall sigma. Sigma, which are quasi-group operations on this set. In other words, I believe that this is what I want to be like the permanent of a 3D hypermatrix, and similar things can be said in higher dimensions. So this sigma isn't a permutation anymore. I mean, the sort of the one-dimensional version of it is a permutation. But when we go up one another level, what we want to say is choose a quasi-group operation, or another way of thinking of this is choose an n by n Latin square. And then what you're going to do is you're going to say, I want this product to be like first coordinate, second coordinate, and then whatever the label would have been on that coordinate in the Latin square. So that is going to give us an n by n permutation hypermatrix, and so the claim is just that all n by n permutation hypermatrices are of this form, that there's a bijective correspondence between these things. And so let's think about this with our example. It's a small example, but it's an example. Okay, so it's like, what would be the Latin square that would correspond to this one? Like, I'm thinking that it's like, so like maybe, the third dimension is telling me my label. So maybe I could think about this thing as being like, it's saying, this is saying something like, okay, if I do like 1 and 1 together, I get something that has label 1. If I do maybe 1 and 2 together, I get something that doesn't have label 1, it has label 2. Alright. Okay, that was a little vague maybe, but did people see what I mean by this? Like, it's like you're thinking of the third direction as being like the label. And so if you do that, you can actually think about going from this permutation hypermatrix to a Latin square, a quasi-group operation, and then you can go back the other way in the manner that I described, by just putting a 1 wherever you see the corresponding label. So hopefully people buy this. So if that's true, then, and also, I mean, also just notice how close this condition was to the quasi-group, the two-dimensional quasi-group situation also. So if that's all good, then see, I would have a little bit of difficulty if I wanted to use this, in the sense that I would actually have to find all of the quasi-group operations on this set in order to do this calculation. Or in other words, I would have to find all of the Latin squares in order to find all of the 3D, to count how many. I would have to actually find all of the 2D Latin squares of order n in order to just count how many 3D Latin squares of order n there are using this formula. Just like here, I have to actually be able to find all of the permutations in order to count the number of 2D Latin squares. Alright, well, anyway, I think that I'm satisfied with this, honestly. I think this generalizes directly. I mean, obviously there's details to check and write out, but like, I'm pretty sure this just generalizes directly. Yeah, that's actually very nice. Well, I guess the thing that's left to do is the thing that would be left to do is to try doing the n equals 2 case to see if it makes sense, because that'll be a good basic test, right? Oh, and then I suppose I'll add in as a comment, if Kaylee and other people have thought about this before, but like, I don't know whether there's any really one definition that people have accepted, but or care about or whatever. But if this is the three-dimensional permanent, then by sticking some kind of sign in here, you should probably come up with a three-dimensional determinant as well. But I'm not going to probably not going to go down that rabbit hole right now, but if there should be a three-dimensional, something that's like a three-dimensional determinant, probably sticking some signs in here somehow should give that to you, right? I'll leave it for you to decide if you can come up with what an even or an odd quasi-group is supposed to be. Or maybe it's not. Maybe you need maybe you need cube roots of unity or something instead. I don't know. But all right. So let's try to actually do this calculation in the n equals 2 case. If I can do it, then I should be able to do it in n equals 2, right? So if we go back to our formula, which as I've now tried to convince you and myself that it's the same formula. Where is this copy of this formula? I have a copy of this thing somewhere. All right, that's all that. Oh, I just didn't go far enough. Okay, so this is the formula. I claim that with my definition of the permanent for an n by n by n hypermatrix, then this formula will still work. But because this n is 2, that means I need an n by n by n hypermatrix whose permanent is at least 2. So I have to think about which possible ones of those are well, which of those exist. And so let's do this thing again. Say here's A, this number of, I think it was sigma lowercase naught, the number of zeros in A, and then the permanent of A. And so, okay, well let's start off with an easy one. Let's make them all ones. So I'm thinking of this as like two 2x2 matrices stacked on top of each other with a bar in between them. So, well, there's no zeros. And what's the permanent? Well, how many of those quasi-group operations can we have in here? It looks like there's only 2. Right? I don't think I can see any more than 2. Well, what happens if I take out if I put a 0, 1 0 in? Okay, this is now 1. Well, as soon as I put this 0 in, it looks like there's only one choice. And I think that it's the same for all the other ones. This is basically the same calculation that we had before. So we get the same exact inputs here. Sigma naught of A is 0, the permanent of A is 2, and there's no there's not any. I think there's not any other terms. I think we end up coming to the conclusion that there should be two of these things again. And notice I already actually basically, so the choice is basically either this is the bottom and this is the top, or you can reverse it and say that this is the top and this is the bottom, and those are your two choices for the two by two Latin cubes of order 2. So that calculation was very similar to the original one and was pretty trivial. So unfortunately, it looks like the next bigger case to check would be n equals 3, and n equals 3 looks like it's already going to be a bit complicated because remember I started to look at n equals 3 a little bit when we were just doing the 2-dimensional ones, and I was like, oh no, I don't want to compute all of this by hand. So I think that I might need the computer to do this. If I'm going to check if my formula looks like it's correct, my generalization, I think I'm going to need the computer to do this because I think I'm not going to be able to do this by hand. But after going through all of this, I'm quite convinced that I mean, obviously my mind can be changed, by evidence that I've made a mistake. But I'm feeling pretty convinced at this point that it's the same formula. Like, just define the permanent the way that I defined it using quasi-group, like the two-dimensional, binary quasi-groups instead of permutations. And it's the same thing. And I claim further that actually the same formula, but instead of doing quasi-group two-dimensional quasi-group operations, there's such a thing as a higher arity quasi-group. The one-dimensional version is a permutation. The two-dimensional version is a Latin square. The three-dimensional version is basically a Latin cube. And I claim that, if you do this definition for like d-dimensional hypermatrices, you want to define the permanent, just use d minus one dimensional quasi-groups and write down this exact formula. Here, I'll actually do it instead of just talking about it. So, in other words, I claim that all of this goes through where if you just use the permanent, say the permanent of an array, which is like a, I1, I2, I3, blah blah blah, up through ID, so it's d-dimensional array, I1, blah 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 blah, ID. You want to define the permanent of that. That's like the new thing that you need. Then this is the sum overall sigma in, I guess I'll say qd minus 1, which are d minus 1 array quasi-group operations on the set 1 to blah 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 through n. So then the product overall I1 blah 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 ID equals 1 through n, and then you have a I1 I2 blah 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 ID sigma ID minus 1. It's d minus 1 area. Okay. So through d minus 1, the product of all of those, d minus 1, and then sigma of I1, I2, blah 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 blah, ID minus 1. And that's the formula that I mean. So yeah. So unless I've missed something, I think that the answer to this in the end turns out to be that the generalization is exactly what the formula was before, except we have to use this definition of the permanent, the definition of what the number of zeros in a hypermatrix is. The number of entries that are 0, that's not a hard thing to generalize. This was a little bit harder, but I believe that this is the correct generalization. Unless I've missed something, I think that this is it. Oh yeah. What is the code? What did you ask it exactly, if you don't mind? Like what exactly did you put in order to elicit a response? And I guess no matter what ends up coming out, I'll know that yeah, well, so no matter what comes out, I'll know that the code or the whatever wasn't stolen from something that I was writing, because I haven't ever actually typed anything out like this before. But yeah, I mean, is the code too long to post, or does Twitch not let you post code, too much code in the chat, or does it not let you post code at all? I don't think I've ever actually tried to post code in the chat. I gotta be honest though, unless somebody out there has actually written a Python code for this already, I have very little faith that this is going to be something that actually makes sense. this is the type of thing that it doesn't do very well unless someone else has already done it before. But I mean, yeah, I'd be happy to see it though. I mean, I guess after this, given that it gave you a response, if it looks at all coherent, I'm gonna definitely try to find the human being out there who already wrote that, because that seems like the most likely situation. It's too long. Well, I mean, I guess you can always try checking it yourself. Or, I mean, I'll be here for another few minutes, so I can if you wanna give me a put it in Pastebin or something, and just post a link in the chat. You know, like just one of those like disposable, like just you want to share like some snippet of code or something, you know. I'll be happy to take a look at it. I mean, I'm not going to run it obviously, 'cause, you know, should just read it first. But yeah, I'd be interested. I'd be interested to see what came out. Because the way I figure it, it seems like there's probably only two possibilities. It's either correct and it's directly copied from somebody who wrote down this code before, or it's just total nonsense. And I'm curious to see which one of those it is. Because this task, especially with that little of information in the prompt, like there's no way. Yeah. Well, anyway, if you feel like doing it, that's fine. Maybe I'll mention too. So the reason why I was saying that it seems like it's not exactly the Rook thing, and why I know that I have an example, is because there are examples. I actually posted about this on Mastodon recently. Let me see if I can just pull up the. Post that I made actually. Let's see, because I know that I posted about this on Mastodon when I was still in Asia, I think, that I had ended up finding this example of a Latin, or there are examples of partial Latin cubes that can't be completed to a full 3D Latin cube, and so let me see if I can find where I myself posted that. Let's see. I know it was recent, so. Okay, I found it. Yes. Oh, okay, we have the Pastebin too. All right, so let me check this out. Oh, Python morsels. Okay. Let's see. This is nonsense, unfortunately. Yeah, so, alright, so here we go. This is what ChatGPT said apparently. So this is unfortunately, so I would have had a hard time believing that there was anything, too intelligent that went on if we had gotten an intelligent answer, because I would have just been like, okay, so where is the GitHub repo where someone has done this, right? But, yeah, it is most certainly not correct. So let's see what it's actually doing. So it claims to iterate through all permutations for each dimension, but if we look here, it seems to have an array of the correct shape. It's a 3D thing, but then we get I, and then the same permutation applied to I in both of these slots, and then we take that and we add it to our total. And sorry, it is actually multiplying those together, but yeah, okay, so that is like vaguely similar, but yeah, I mean that's about the extent of it. it's just, yeah, I mean, it's so basically all that we've acquired here is about the level of like, I know that I'm supposed to do something like the permanent, and there's code for the permanent online, and I know it needs to be 3 by 3, or sorry, not 3 by 3, n by n by n. It needs to be it is 3 by 3 by 3 in this example, right? So it puts in some boilerplate, which is like the boilerplate that you put in when you're messing around with the the shape of a hypermatrix and numpy or whatever, right? numpy, whatever. And this is just nonsense, unfortunately. But any day now, it's gonna take all of our jobs for sure. Just a few more years, and it's really gonna get us, huh? Anyway, yeah. So, you know what's even more funny now, right? If me or someone else goes and then types into like some GitHub overleaf, like some system that's selling all of our data to these companies, types in the correct thing, then in the future they'll say, "Oh, our system wasn't smart enough to write Python code to compute the permanent of a hypermatrix before, but now it comes up right away." And of course it comes up right away because we did it, but every day there's a new sucker is born every day, and you just tell them, "Oh, look, it's even smarter than it was before." Those people they're just naysayers. They don't want to lose their jobs because our system's so smart. Well, anyway, I shouldn't be so mean. I hear that the investor money is drying up a little bit, so I should just be happy that the winter is coming and just be at peace. But all right. Well, anyway, I will have to code it, and that code at some point will be absorbed into whatever the big data set is that things are trained on. But we're not there yet. Okay. Oh, I was going to show you the reference that I found. Okay. So this is here. I'll just show you my browser screen. Oh, that's not the right shape. I posted on Mastodon a little while ago. I know some stuff about Grothendieck, but I don't know the story about him leaving the institute. Yeah. I still have time to become an angry communist, right? Like it could still happen. I don't think I'll go bald though, probably, but you never know. Yeah. So let's see. Oh yeah. So I posted this, and so I did find what I was looking for. Okay, so it was a 1995 paper that was relatively narrow Latin parallelepipeds. Try saying that 3 times fast. That cannot be extended to a Latin cube. And so there's an example. There's infinitely many examples, but there's small examples where you can have partial Latin cubes of a given size which cannot be completed. Oh no, now I'm second guessing myself, because I realized that partial Latin cubes are not. That's right. Oh, okay. Partial Latin cubes are not the same thing as partial arrangements of rooks in 3D, because a Latin cube corresponds to a bunch of arrangements of rooks that are like complementary to each other, right? So having a partial Latin cube means you have a bunch of arrangements of rooks which are complementary but maybe don't go together to fill in every spot, right? So it's possible that there is actually always a way to complete a I'm not sure, but I feel like the existence of a not completable partial Latin cube means that there should be a not completable arrangement of rooks. At least in the next higher dimension, I think, because that's right. Because if we have a wait, you think it's the same? like you mean, okay, wait, what's the same? You mean that there is a bijective correspondence between, or like, are you saying that, okay, a Latin cube, right, a Latin cube is a four-dimensional work placement. Okay, so this doesn't answer the question of whether there's a not completable three-dimensional, oh, no, but it's bijective, how do I want to say this? No, I should be careful. Every Latin cube gives you a four-dimensional rook placement. Every 3D Latin cube gives you a four-dimensional rook placement. So a partial Latin cube is a partial rook placement. So it's saying that there is a four-dimensional rook placement that can't be completed. But that still leaves open the question of whether there's a three-dimensional rook placement that can't be completed. Because, well, it's true that every two-dimensional Latin square would give you a 3D rook placement. We want to go in the other direction and say that but what if there's a 3D rook placement that can't be if I have a 3D rook placement, does that have to give me a Latin square? That's the question. And I'm not sure that it does. Right, because it's like two different kinds of questions, right? Like if we know that there's a non-completable partial Latin cube, then that means that there's like a non-completable partial four-dimensional rook placement. Oh, right. I totally missed that. I saw that you said it, but I just didn't process that, because then you're saying that you're using the partial. You end up actually counting the partial rook placements anyway. Oh, I understand. Okay. So it doesn't rely on it being completable, because you're saying that so what is the quantity that was being counted there? Was it actually the number of like those, like, not just maximal, but like maximum rook placements, where you have, like, in 3D it would be that you have n squared of them? Is that what's being counted? Right, but that doesn't answer the question of whether there's a maximal three-dimensional rook placement that doesn't. Okay, so what you're saying is, if I take if I had any rook placement, whether maximal or not, and I project down, that will be a partial Latin square. Oh, I understand. Okay. So, yeah. So if I try to fill out a table, that's like, well, okay, I guess I don't really have to do these, but okay. So if I have a partial thing that looks like 1, 2, 3, right, and this is supposed to be 3 by 3. Okay, this can't be completed to a Latin square. A 3 by 3 Latin square, right? It can't be completed. So when you go to the three-dimensional rook placement, right? It's like saying, okay, we have something that's in the one, maybe the bottom level is like the one level, so you have like a 1 here, and then you have in this position you have a 2. And then in this position you have a 3. Okay, so what this is saying in the Latin square situation is that you can't put in any entry here. So over here, that's like you can't yeah, you can't put anything in this column. Oh yeah, so I mean this is a maximal on the 3x3x3 board, this is a maximal arrangement of rooks, which does not have it has far less than 9 possible things. Yes. So then there are, okay. So so is this maximal? Is this counted in your count of how many of the maximal arrangements of rooks there are? Because if it is, then this is not something that I wasn't directly considering these, you know. Certainly it's not, you know. It's definitely not a you know, it doesn't correspond to a quasi-group, right? Well, anyway, I mean, also, I guess I don't have a ton of time left, but feel free to send me a reference too if like there's something that, you know, or I guess if I just look up like the rook problem for the higher dimensional rook problem, I should see, but yeah, do you remember if the permanent was explicitly used? How many arrangements of k rooks? Well, it wasn't how many arrangements of k rooks exactly. Like the version, so the permanent would count. Yeah, so the permanent would count. It's counting how many arrangements of. So in the 3D case, right? If it's n by n by n, the permanent is counting how many arrangements of n squared rooks are sitting inside. This is like the largest possible number that it could have, or yeah, n squared. This is like the largest possible number that it could have. Let me think about this. Or is it n? No, n squared. Sorry, the switching the dimension is making me feel like I'm off by 1. But yeah. So if you're looking at, okay, so if the question was like how many arrangements of k rooks for any k, and that has been answered for all k, then what I need is a special case of this thing. Okay, yeah, right, because if I go back to this formula, right, like yeah, for each choice of these, yeah, it is n squared, right? Because for each choice of these coordinates, I have a rook that is the one rook in that column, if you want to think of it that way, in that like 3D column, yeah. So if you know that number, then that's the permanent. So is there like a lot that people know about that quantity that is not just like that? It's like the higher dimensional version of the permanent, or oh, it's just I understand now. It's just the 2D case has been done before. All right. Well, see, now I get to be the person who says, okay, if anyone ever tries to do anything like this and publish a paper on it, then I get to say, yeah, I sat here for one time in 2024 and talked to some people on Twitch about it for a few hours, and so I own this now, and this is my idea, and you know, no one can publish on it or whatever. That's not really how it works, by the way. Like they would just be like, you know, we actually have an original contribution. That's not just this. Oh, that it would avoid. Yeah, so there are other papers, which I don't have right at my fingertips, but there are other papers that give other methods for computing the number of Latin squares. So that's something that exists. I don't know what the other methods are. I actually have no idea. This is the only one I've seen. It's the only one I've messed around with. Yeah, so it's possible that there is a way to generalize some of those that avoids having to actually find all of the n by n Latin squares first. And like also, I said you could do this, in higher dimensions too, like beyond 3. At each level for d dimensions, you have to know what all the d-1 dimensional Latin cubes are. So like it's definitely a bad situation, you know, because it's not even just that you have to use the formula like iteratively, right? It's that you don't just need the number, you need actually what they all are specifically. So like this is basically totally useless from a computational standpoint. I mean, assuming that you couldn't figure out how to eliminate a huge amount of cases or something. Yeah, so this is disappointing in that sense, but the nice thing is that it seems like it does directly generalize, so at least we have a formula that in principle we can work with. And who knows, it might have some use, some nice use that is not actually just getting the number directly, but is something else that is useful to do. So you know what else? I mean, this is just a note. I mean, I guess whatever it means for it to be a note, but like, you know, these people really could have just said, well, we're gonna just do this for, you know, for n-dimensional Latin cubes and, you know, d-dimensional Latin cubes instead, and it would have seems like it would have been pretty much all the same thing. All right, well, it's about that time. I really appreciate everyone's comments and questions and feedback. I hope you've, you know, continued to get a lot out of listening to me rant, and, you know, seeing me actually do some mathematics from time to time. This is kind of a natural stopping point for this, but I don't know. I mean, maybe either on Mastodon or some other way, you can always let me know what you think maybe I should do next week, or if you want to see more of something I did before. I really have a lot of fun doing this. I've continue to have so much fun. I'm glad that we were able to all talk about this. Oh, Dobby, it's okay, buddy. All right, Dobby is having some kind of concern over here, so I better go attend to that. I hope you all have a wonderful rest of your day or night or whatever it is, wherever you are in the world. So I'll see you all next week. Goodbye.